one. I mean, for people who have worked with SPSS, for example, you can code male as say 1 and maybe female as 2. You can code true as 1 and false as 0, something like that, right? So categorical variables are generally coded because you know that there are only a few possible outcomes, and we'll see how R handles all of these things. R handles them specially, and it is very, very important, very basic that we understand how R handles this thing because they give us solid foundation to our R experience, all right? And let's also not forget that the type of analysis that you do depend on the type of variable you are dealing with. For example, you ordinarily cannot do addition on text variables. You cannot be adding my first name to my second name. What's that going to give you? But you can add numbers, right? Okay. The other thing we should know, which people really find amusing sometimes, is when I say variables can be converted from one form to another. And we do this very frequently, right? We convert age and we bin it and we call it age group. 0 to 5, 6 to 10, 10 to 15, or something like that. And we're already converting our continuous variable, which is age, to categorical variable, right? Because now there are only a few possible outcomes. But generally, as much as possible, please don't bin your continuous variable on the field, all right? And this is one of the main reasons why we say that. Let's say you have 2 ages, 12 and 13. When you bin, they both belong to 10 to 14 group. But for some reasons, you need to get the original age back. How are you going to know whether any of them is 10 or 11 or 12 or 13 or even 14, right? So it's always easy to get your bin or grouped variables from your continuous variables, but you cannot get your continuous variables after you have done the grouping, all right? So please, always have your data as continuous variables if that is what you have collected on the field, and don't start doing pre-analysis before you get to the analytic stage of your research or of your analysis, right? So we have a few charts that are quite common. The type of chart, again, that you will use depends on the type of analysis that you're doing. Generally, you use bar chart for categorical variable. For example, I want to know how many are male, how many are female. I might use a bar chart for that. Histogram I use for continuous variables. For example, I want to know the age distribution of all my respondents. Histogram is really going to show me how they vary, how many of them are on the lower side, what's the lowest age group, what's the highest age group. I'll probably expect most of my respondents to fall at the middle, right? If you want to look at 2 continuous variables, how they vary, how they relate to each other, then you'll be looking at scatter plots. When you want to do trend analysis, then what you'll be doing is a line plot. Box plots, I won't talk much about it, but they're really very useful when you want to look at summary statistics across a few variables. For example, I want to see let's say I've collected data in 3 states in Nigeria. I'm just going to, for the sake of those who are not Nigerians in the group, I'm just going to say Abia State, Taraba State, and say Benue State. Those are 3 states in Nigeria, and I want to see how the age varies, the mean, the median, and things like that across the 3 states. Then a box plot becomes very useful because it shows me the variation of age across the 3 states that I've mentioned. Pie charts are also used, but my teachers taught as much as possible to avoid pie charts, and we can still go into the details of why you should avoid pie charts as much. Generally, in the analytic phase, we say avoid pie chart as much as you can for so many reasons, all right? But it's worth mentioning that, yes, pie charts is also possible, all right? So some of the statistics you might want to do, now this is taking us back to high school, measures of central tendency. You might want to do your mean, median, mode, which are descriptive statistics. You might want to check your standard deviation, your variance, the range, and the interquartile range, which are your measures of dispersion. We're going to see a few of the measures of central tendencies tomorrow. We're going to be calculating the mean age, the mean weight, and things like that. Inferential statistics, that's when you start doing your test of hypothesis, when you state your null hypothesis and alternate hypothesis. This class is really not going to cover, it's not going to cover inferential statistics, but I can assure you R is extremely powerful when it comes to inferential statistics. I have another slide for all together, basically for introduction to biostatistics, which is a bit more detailed and has some practice examples. So if you feel like trying your hands on them, please feel free to just check them out when you have the slides. All right, so that's a bit of statistics for practically all the statistics that we'll be needing for this class. So we're back to R again. All right, so welcome back. Now, we're talking about R functions. R functions are basically how you interact with R. When you give R an instruction to do, then you're probably going to be passing that instruction by writing a function, right? So I can perform simple arithmetics. I can just copy this. We've done this 1 + 1 before, but I'm just going to do it again. I'm going to open this up. Okay, and then yes, we still have it here, and I can do 1 + 1. I can do my 4 divided by 2. I'm going to send it to the console. I just press run. Okay, so I can do these basic ones, right? But the majority of the things you'll be doing in R are you're going to be using a function that looks like this. A function name followed by an open bracket, the data you want to apply it on, and what we call some set of arguments, all right, to that function. And then you're going to have your closing bracket. And I'm going to give us an example. Let's assume I have a group of 10 people. I have numbered them 1 to 10. But I want to sample 2 of them. For some reasons, I want to sample them with replacement. So I could call the first person, take the person back to the group, and then if I sample again, I might just be lucky to sample the same first person for the second time, all right? So more or less like sampling with replacement, a group of 10 people. So the function is going to look like this. Now the function name is called sample, unsurprisingly. And then the data I want to sample is 1 to 10 people, all right? So this column represents 1 to 10. I'm just going to come to my console now so that we see that it lists out 1 to 10. We can see it's saying it has listed them out, 1, 2, 3, 4, all the way to 10. So I'm telling R, I want to sample 1 to 10 people just twice. But this time around, I have said I want to sample without replacement. Don't replace, meaning I don't want to get the same number. All right? So if I change this replace equals true, it means that I might just be lucky to get the same number, right? So if I just copy this, put it on my editor here, and I send it to the console. So we can see R doing my sampling for me, all right? And it has sampled my 1 to 10, and it's giving me 3 and 6. If I run this code again, I'm going to get a different result. I run it again, sorry, if I run again, I'm still going to get another result. So that's basically how the functions work. So again, there's going to be a function name. There's going to be the data you want to use it on. And then there are going to be a few arguments, right? Now, a few things we should know. Sometimes we have some functions that they don't have any argument. For example, there's a function called system.date. Letter S, capital letter D, system.date. And what it does is that it checks my computer and tells me the date on my computer. Of course, today's date is 11th of October 2021. And then it prints it for me, all right? There's another function called dates. And then it prints the same system date, but in a different format, right? There's another one called system.time. It checks both the date and the time on my computer, and then it puts the time zone. As you can see, all these examples, they are blanks, they don't have any arguments. And that's because they are not needed, all right? So there are a few functions like this, be aware of them. And then some questions might come as to, oh, how do you know the type of functions to call? Don't worry, you're going to build your grammar over time. So you're going to build some of these functions and you will know when to write. So It is also important to know that some functions don't have a name. It's not common. We call this anonymous functions. We might see one or two, and we might not see it at all. But I want us to just know that even though I said generally functions have names, a few functions may really not have name, and anonymous functions. All right. Now, functions don't exist all by themselves. Functions are generally contained in packages. So what are R packages? R packages are just a collection of group of functions that do similar tasks, right? So take, for example, I want to do plots. There are probably going to be a group of functions that help me to be able to plot my charts. And all these functions may be in one particular package, all right? So packages, again, contain group of functions that perform really similar tasks, all right? Every function in R belongs to a package, no doubt. Every particular function that you see in R belongs to a particular package, all right? So some functions come pre-installed with your computer. The moment you download R, it comes to some basic, what we call the base R functions. So those are the minimum to get you working. Probably more than 90% of the functions that exist in R, they don't come with base R. You have to install them. They come separately. So that's why I said before, people develop and contribute codes to make R better. Most of these codes are contributed as packages. For example, there used to be one very dull, not so beautiful plot that we used to do in the past. Okay? Basic plot in R is really not so beautiful. And then somebody came up and said, you know what, we can make R a lot more beautiful. I mean, R plot is a lot more beautiful. So put all those functions together and call the ggplot2 package, which we're going to be seeing tomorrow. Then it gives us functions, access to all these beautiful functions, lovely functions that helps us to produce lovely, beautiful graphs, right? And then somebody said, oh, these functions are, these graphs are beautiful, they are lovely, but they are static. You can't interact with them. You can't deactivate, activate. Oh, I'm going to do something interactive. Put all those functions together again and say, oh, I give you some bits of interactivity, all right? Calls that another package. Again, what I'm saying is that the moment you install your R, it comes with some basic functions. These functions are in some packages, but most of the other things you'll be doing belong to other packages. I'm just going to take a minute to stop sharing this, and I'm just going to go back to the data that I'm into, the zip folder that I shared with us previously. And I'm also going to show us how we did that. Okay, so if you remember this particular place, the instruction says that we should open this R folder and click on this package installation, which open this place up. And we can see what we are doing here is we're installing additional packages, a lot of them, even though these are about 6 or 7 of them that we wrote here. These actually have installed additional helper packages. And for some of us that have run this script already, we can see that it probably took a few minutes, 5 to 10 minutes or even more, before this process completed, because it just kept installing packages and packages and packages, right? Okay, so again, packages helps to improve the functions that are available for us in R, all right? So how do you go ahead to install packages? Most of these packages that you'll be installing them from what we call CRAN. If you remember, CRAN was the same place that you downloaded R, all right? It's also the repository for all validated packages. So what you need to do is just call the function. Again, like I said before, most of your interaction with R will be via a function. And not surprisingly, again, this function name is called install of packages. And then you're going to put the name of the package you want in quotation marks inside, right? Or better still, that we'll be looking at tomorrow, we're going to be calling the p install. Like I said, we've always had the install.packages, but somebody said, you know what? It's not as good as we would want it to be. I'm going to improve the functionality of this, and then it created the p underscore install function. That does, in my own opinion, a lot better than the traditional install of packages, right? So you just do p install, and then you put your package name. But this p install is a function that does not come with your R. It is actually in another package called man. So it means that you have to install pacman before you can use the p install function. Again, let's not get worried, or let's not get lost in all of these things. Basically, what I have just said is this. If I want to use the p install function, if I call p install, I'm just going to call, I'm going to put the name of the package here. If I run this, it's going to tell me that it cannot find the p install function. Like I said, that's because p install does not come pre-installed with R. It's in a particular package of its own. All right. And before I can access this p install function, I will have to load that package where p install is. Fortunately, I know that p install is in a package called pacman. Load a package you call library. That's the library function that you use. So I'll just do library pacman. So I'm going to send this to the console. It's not going to show anything. But now, all the functions that are in pacman have suddenly become available for me. So I can now do p install pacman. And we can see it's already working now. It's saying installing package into this. I'm going to stop this because I already have the tidy package, and there's no need for me to reinstall it. All right. So basically, that's how you do it. So you call the library, and then you use the functions inside the packages. Okay. I know it's so much already for us to handle today, so we're almost done. And again, these slides are already available, so I'm just going to, after this particular class, we're going to have access to this slide. I'm going to put the link, and I'm sure that the host will also communicate where these slides are for us to use. So I will have access to these slides to basically be able to go over this thing before the next class. All right. So now, most of the things we have done were practically executed. For example, these are 4/2. It just give us our results 2. What if I want to save this value 2 and I want to use it again? Let's say I want to say, like we used to do in algebra class, if x is y, x is 2 and y is 3, and then z is x plus y, what's the value of z? So let's just write something like that here. We have said if x equals 2, y equals 3, what is the value? Z equals x plus y. What is the value of z? All right? So how do I now write this in R to make sense? I can't just do this. This is English, right? Or more or less like narrative. So I have to save values. It means that I have to assign the value of 2 to x, and then I have to assign the value of 3 to y. So I can say, give me z as x plus y, and then tell me what is the value of z. So how do I do that? So generally, this is how you assign values in R. Okay? You can use the equal operator sign, the equal sign. All right? I need to comment this out. It's creating the error. If I do x equals z, I can come to the console and say, what is the value of x? It's going to tell me that it's 2. Okay? But we generally don't use equal sign. What we use is this weird looking symbol, a combination of less than followed by hyphen. All right? There is a shortcut on your keyboard. You just press Alt together with the minus sign, and it's going to put it there for you. alt together with your minus sign. It's going to put it there. And the reason why we use this symbol is because we don't want to confuse ourselves with the equality sign by testing whether x and the value on the left and the value on the right are the same, which will give you either a true or false. So R traditionally uses this to assign values. So let's say we have assigned the value of 2 to x, right? And we're assigning the value of 3 to y. Now, somebody asked a question previously. He said, what is the usefulness of the environment pin? So we're going to see that now. You see that everything I saved into memory goes into my environment. All right, I can see in my environment now that the value of 2 has been given to x. And if I send y, I can see that y has also appeared with a value of 3. I can now say z and assign it the value of x and y. So if I send this to the console by pressing the run button here, you see I have x in my environment now, and it tells me that the value of z is 5. So I can come to my console and say, okay, give me the value of z. And then it's going to tell me, oh, I know, z is 5, right? So this is how you assign, okay? I can also assign other things. Let's say my name, Stephen Balogun, right? If I send it to the console and I look at my environment, I can see that my name is now there and the value is Stephen Balogun. Now note that I actually did quote my name, right? Texts are generally quoted in R. If you don't quote it, R will think it is an object that exists in your environment, and it is come to your environment and start looking for, oh, what value has this particular thing? I mean, what's the name that has this particular value? I will start looking for it in your environment. But because this is not in my environment, it is a name that belongs to me, I have to put it. All right? Generally, when you are assigning names in R, a few instructions come to mind. Your name can be a combination of letters, digits, full stop, or underscore. As you can see, I have used letters and underscores here. I could put one at the end and it's still going to really work, all right? But we say generally use what we call syntactic names. Now, syntactic names are this: a combination of letters, digits, full stop, and underscore. Any is fine. It doesn't have to be all, but any of them is acceptable. But a syntactic name cannot start with a number. If you are starting with a full stop, then that full stop cannot be followed by a number. You cannot put space. For example, I cannot say my name and give it this. You cannot have space when you are assigning names, all right? You can see unexpected symbol, it gives us an error. Spaces are not allowed, and there are a few words that we call reserved words. You're going to see a few reserved words, but a few of them are like this. No, you can't give no. You can't say, you can't give an object the name of no. True, you can't give true to an object. No, you can't save a value with true because these are already special, they have special meaning in R, all right? So if you want to know the reserved words, just do your question mark reserved, and I will pop up a list of all the reserved words, and you will see them, right? So again, the question mark is an helper function that brings up the help page in case you want help on anything in R. For example, if I do this, we're going to see that the help panel here has opened, and R is telling me about all the reserved words, and we can see all of them: if, else, repeat, while, this, about 19 of them in all, I think. So these are all the reserved words in R. You cannot use any of these to save an object, all right? The same thing, you can call help on any function. For example, we have used sample previously. I can put the question mark sample, and it's going to tell me how sample works. It's going to give me a description of sample. What does it do? It's going to tell me how you apply it, and you can see all the arguments that sample takes, right? It's going to also explain each of the arguments to me. What is X, what is Y, what is Z, what is this, what is that? And then it's going to go into a detailed summary, and it's going to finish with examples. Really very helpful, right? Okay, so that's also available for us. So this is how you do assign values in R. So basically, there are two schools of thoughts in terms of naming conventions. There is the snake case naming convention and the camel case naming convention. The snake case is saying when you want to assign a name, replace every space with an underscore. So I have the example here. This is the snake case. And that is why I have this my underscore name. Ordinarily, it would be my space name, but I'm putting it as my underscore name. So two things in snake case. Every letter is in lower letters. Replace every space with an underscore. Just those two things in snake case. Camel case says, you know what? We don't want spaces. Delete all spaces. The first word will all be in lower letters. Every other word after will start with a capital letter. So I would have written it as my capital letter N, and all the rest will be small letter. So this will be camel case, basically because it is said to look like the hump of a camel's back. So that's why it's called the camel case. So this is how you do naming. These are the two common schools of thought when it comes to naming conventions in R. Generally, I recommend using the snake case. All right. We have just a few more slides, and we'll be wrapping up for today. So we've talked about functions in R, we've talked about packages and how you do all these things. But if you recall, we talked a little bit earlier about variables, and we said we have the numeric variables, we said we have the categorical variables, and then we said we have the text variables. Now, R builds up its data using something similar to that. We call them the vectors, all right? And they are the building blocks in R. There are four common ones, okay? And I'm going to really be linking them to what we have learned previously about variables. Integers. Integers are just discrete variables. They are whole numbers. They are always, they are always whole numbers. They don't assume decimal places, which is equivalent to our discrete variables. If you really want to tell R that a number is an integer, you will need to put, if you are writing just one single letter, you will need to put L at the back. Okay, so if I write something like 10L, R will assume that, okay, this 10, but you are telling me that it is not a continuous variable, it is a discrete variable, an integer. That's why you are putting the L at the back, and it's going to understand, and it's going to put it as 10, but at the back of its mind, it's going to know it's an integer. Now, this is very, very important because we say that continuous variables, which R calls double, double, that's the equivalent of continuous variables in R. We say they are really not absolute numbers. We call them floating numbers. Now I'm going to give us a classical example. What do we expect the value of, if I say 1 divided by 49 times 49, what should be the value of this? Can I put it in the Abraham, just give us a minute. I'm going to show you how to get your editor out. Basically, what you need to get your editor anytime is either to come to your file, is either to come to this plus button here and open an empty script, and it's going to bring out your editor. Or if you already have a script, you just open it and then you will have it pop up. Excellent. Thank you, everyone. The value is supposed to be 1. So let me check if this is actually equal to 1. We're going to talk about this equal sign in a bit, but that's the check of equality. I want to check if this is actually equal to the one that you have told me about. And what does that tell me? It says, no, it's not. It's false, right? It says it's false. And basically that's because there are internal approximations that happen. When you do 1/49, it actually gives you to so many decimal places, more than 16 decimal places. All right. So in the end, R will have to approximate, right, to the nearest number of digits. And by the time you multiply that again by 49, it does not absolutely give you 1. It gives you something close to 1, 1.0000000 something, but it's not 1, right? So that's the concept of double. We say they are floating numbers, all right? And you will learn how to deal with something like this in a bit. But this is just to let us know that when you are dealing with integer and you want R to know that, no, this is a whole number, you always have to state it categorically as such, that R, this is not a continuous variable. This one is a discrete variable. They are integers. They are always whole numbers. So you don't do this kind of approximation, okay? The other common building blocks that we have, data types, the Boolean or the logical variables. These ones are basically one of two, either true or false. Those are the two common logical variables that you have, true or false. And we know that generally, true is coded as 1 and false is coded as 0. So because of that, it is possible for me to add true and true together, right? Or I can add true plus false, and add false plus false, right? I can do arithmetics with logical variables because, like I said, true is internally coded as 1 and false is internally coded as 0. So if I send this to the console, we can see that it gives me the value 2, right? And then true plus false gives me the value 1 and false plus false gives me the value 0 because of the internal coding that occurs to Boolean variables, right? So characters are our texts, strings. Now, the very important thing that I want us to take on with characters is this. Characters are not just letters. They are not just alphabets. They are anything in R that you surround with quotation marks. Okay? So even if I write the number 11 and I surround it with quotation mark, I will assume it is a character. If I write capitals true, I surround them with, I surround it with quotation mark, I will assume it to be a character. This is very important because sometimes it causes confusion, all right? And we're going to see more about that in a bit, okay? So you can have something like this, Stephen, 12, and true. All of them are seen as characters because each of them are surrounded with quotation marks. The other thing I should quickly mention right here, right now, is that please, R is extremely case sensitive. If you write something as small letter right now, and in the next few minutes, write it as capital letter, R is going to throw an error. And I'm going to give us a very, very common one. System.date. I've shown us this function a few minutes ago. The S here is capital letter, and the D is also capital letter. If I execute this, this is going to work. But for any reason I write this first letter as small letter S, this is going to throw an error. And it says you can't find it because it's extremely case sensitive. So you need to be careful. Sometimes changing the case of just one letter might give you a headache, might be the source of bug in your code. It might take you a while to be able to figure out. So please be careful with your cases. And that is one of the reasons why we generally prefer the snake case convention, because everything is written in small letters. And you don't have to worry about what have I written in capital letter, what have I written in small. Everything is just small letter, and just keep writing it that way. Unfortunately, some functions come like this, and you will have to use them. You have to be familiar with which ones are capital letters, which ones are small letters. Two other common building blocks in R exist. We call them the complex and the raw. I won't mention them today because they are not common, all right? And we'll probably not work with them for a very long time. These are more or less like useful for people who work advanced R users. Let's just put it that way. And you probably will not have you probably not even see um, data presented to you in this form for a long time. All right. So one more thing about the building block scenario that we quickly need to talk about is that there is hierarchy in vectors. All right. So if you mix vectors of more than one type together, you recall that we said there are four common ones: the integer, the double, the logical, and then the characters. I will force all of them. If you mix them together ordinarily using this C function, I will force all of them to assume a particular type. And this picture here shows us the hierarchy. Logical is the weakest in the group, and numeric variable together. I will force all of them to assume numeric, and I'm going to show us right now. Okay, so I'm going to do C function true, and I'm going to write 10, and I'm going to send this to console. Recall that we have said true is logical, and 10 is either it's the double. If I put L at the back, then it becomes an integer. If I send this to the console, you're going to see that this true will become 1. All right. And that is basically because I will force them, all of them, to assume the same type. If I put the same true together with my name, Stephen, you're going to see that I will end up forcing this true to assume quotation marks. Okay? Now we can see that now there are quotation marks around true. Because especially when you use this C function like this, what we call vectors, all of them must be of the same atomic building block. All right? If you mix anything with character, I will force all of them to assume character. If character is not there, then numeric variable becomes the next higher up in the ranking. All right? But we've talked about four common ones. I've not talked about categorical variables. How does R deal with categorical variables? Okay, so there are what we call augmented vectors in R, augmented atomic vectors. They're more or less internally one of these four common ones, but they have a special modification. Okay, so the first one is the categorical variables that we call factors. Recall when we were talking about factors, we said factors are generally coded. We can code male as 1 and female as 2. All right? So and that's because factors are coded as numbers. So internally, factors are seen as integers. So your categorical variables are seen as integers. But you cannot just write something like male, female, and expect R to understand that these are factors, because R should know that you can only be one of male or female. No, it doesn't work like that. I will take this as characters. You will have to tell R that, oh, these ones are factors. So, and then we'll see how you do that in a bit, right? So how you just do that is that instead of this, you call it a factor function. And then you're going to tell R, make these two things as factors. And then I'm going to send this to the console. Okay, right? And then I'm going to come here and tell R the two levels that it may have. Levels equals male and females. So I'm saying there are only two possible levels, right? So if I send this now, okay. Oh. Right. So this tells R that, okay, you're telling me to change these things to factors. Right? And R will do that, and then we'll have this coming up as factors. Hold on. Okay, so I missed the first quotation mark. Okay? All right, so I think everything is fine. All right, so we can see R is telling me, all right, I understand that you have changed them into factors, levels is 1 and 2. All right, so this for factors. How about date? Date is one of the very interesting things in R. All right, and this is an example of the date. I've written this a couple of times already today. Are these integers? Are these double? Are they logical variables or are they strings? Are they characters? Though they are surrounded by quotation marks, but internally, dates are doubles, are numbers. There is something called ISO 8601, which is the standard, the international standard adopted for date format. It's saying that you write your date in 4-digit year, hyphen 2-digit month, hyphen 2-digit date. And that is how R will always, the conventional R will always write your date for you. 4-digit years, hyphen 2-digit month, hyphen 2-digit date, because R follows the ISO 8601. But one particular thing you will see is that if I tell R, what is, okay, let me assign date to today. I'm going to assign it as system.date, like I said previously. So if I print today, it's going to give me today's date, right? There is a function called type of. Let me come back to my editor here. If I call type of is a function that lets you know what is the type, vector type that I'm dealing with. Is it a double? Is it an integer? Is it a logical? Or is it a character? And you can see that R is telling you that, oh, I understand, even though it is a date, but I understand that internally it is coded as a double. The same thing goes for time. Time are also internally coded as double. Duration is also internally coded as double. So these are the 4 common augmented atomic vectors that we have in R. So what happens if I want to have a mix of different vector types together? Is it possible? Yes, it is possible in R, but then you will have to use what we call a list. You have to create them as a list. So when you create a list, you're telling R that I'm creating different things. I understand that they are different. And I also understand that you won't want to mix things up. Okay? So I'm going to keep this for you and I will not mix them. So you use a list to create something like this. And you see, when you send a list to the console, see how it is printed. Now it's telling you, I understand that you have added 3 different things together. All right, the first one is this, the second one is this, the third one is this. And if you notice, R didn't quote my true, neither did it quote my 29, because it's knowing that, oh, they belong to 3 different things completely. You have given me 3 different lists. I'll keep them separately for you. I won't keep them together. All right. So if for any reason you have to mix vector types, then you will have to create a list, because list can hold anything for you and it's going to keep them exactly the way you have given it. It's not going to force them to assume anything. Now this becomes very interesting because data frames, most of the data type that we have, they are a special type of list, right? But today I see a question, the difference between the standard brackets and the square brackets. Let's just finish today's class and I'll see if I can talk about that. I would have probably wanted to avoid it, but because somebody is asking, I'm just really going to mention it. As much as possible, I want to stick I want to stick to what I think is the purpose of this class and not really digress, but I'm going to take that question at the end of this class. And we're going to do that out, right? So I'm just going to print an example of data frame for us. You probably are not aware of this, but there are a few data frame comes reinstalled with R. There's one particular one called empty cars. Empty cars is just looking at fuel economy of some cars, but it's for over a few years ago. All right. So what I've just done is to print this data frame, and I just want to use it to show us. This is a regular tabular data, rectangular data, where we have columns and then we have rows. So what I've done is that I can see here, it's telling me a little bit about my data. It's telling me it has 32 rows and 11 columns. 32 rows, 11 columns. I can see all the columns here. And then I've printed only the first 10 rows. All right. I'm not printing everything, just printing the first 10. And if you look at the top here, it's telling me the particular data type of each column, right? It's telling me that MPG, which stands for miles per gallon, is telling me it's a double. This CYL is telling me, which stands for cylinder, is telling me it's also a double, and the next one, and the next one, and that like that. So I can see the type, right? The vector type of each of these columns. So basically what I'm trying to say is that a data frame is just different lists put side by side, all right? Or more or less like different vectors put side by side. But a few convention for data frame. The first one is that all of these columns must be of equal length. All right. So each of these columns must have 32 entries. For example, in this data frame, each of the column has 32 entries. That's number one. If it is missing, it is better to put missing there. All right. Or R will automatically tell you that not available. The data for that particular column is not available. But each of the column, all the columns must be of the same length, all right? And each column can only take one type of vector, all right? Of course, you can have a list as a column, but generally, each column has a special only one type of vector. For example, as you can see here, each column is a double, right? We're going to see this a lot when we have our data tomorrow. Now, we're probably just going to take a look at our data and see how it looks like as we wrap up this class. Okay. So I think I've mentioned a lot about type of. Type of allows you to know what type of vector are you dealing with. So you can call type of 10. Type of Stephen will tell you that Stephen is a character. So I'm just going to copy this and I'm going to paste it in my console and we'll see that it's telling me it's a character. If I do type of untrue, it's going to tell me that true is a logical variable. All right. So somebody just in the chat box, tell me, what do you expect of this type of? I'm going to copy it and put it in my console, but I won't press enter yet so that somebody will tell me. Yes, somebody said text. Who agrees with somebody said character, text? Okay. All right, so I think we're all correct. There's actually character, but we have also said characters are text, all right? Strings are also text, all right? But what is important is that I want us to know that because we have put this in quotes, this false is no longer a logical variable, right? I think we've said this before. Somebody is asking, what's the difference between typing in editor and typing in the console? I think I've explained. I'm just going to do that again right now. I can easily clean what I have written in the console and I use everything. But when I have it in the editor, it saves. The other thing about the console is that if I keep writing in the console, over time, I'm going to lose track of all the things I've written because it's going to keep scrolling up. So and sometimes I make error. For example, like I've written this one, I can't go back and correct it in the console, but I can easily correct what I've written in the editor and I can also save it. I can save it somewhere on my computer, but I can't save something on my console. So that's why we prefer to write in the editor and not really in the console, okay? So yes, the next question is that, let's assume that I don't know that this particular vector is a double or an integer. How can I check what kind of vector it is? You can use is dot and then followed by the atomic type. For example, is dot double 10 will tell me, is this a double? And then of course, because it's a 10, I expect it to be true. All right. So I will tell me yes, 10 is a double. If I say is this a double and I put true there, I will tell me false because true is not a double, true is a logical, right? So arrow is going to tell me false, right? So that's the is dot function. But sometimes yeah, you might make a mistake and then you might have somebody write 10 and put it in quotes. All right, how do I force arrow to say, oh, this is not a character? Then there is the as dot function, all right? So the as says, oh, I want to force this particular thing I put in my brackets. I want to force it to be an integer. And then R automatically removes the quotation mark, all right? So if I put it as dot logical, I'm going to get any because this doesn't make sense, all right? So I cannot force something like this to be as logical. But if I remove the quotes and I put 10 and I do as logical, I'm going to get a true. Anything more than 1 is true, all right? I mean, anything more than 0, any value not 0 is true. Anything greater than 0 is true. So if I won't have to force any value greater than 0 to logical, it's definitely going to give me true. It's only 0 that is going to give me false. I mean, yeah, and we can see right there, it gives me false. So the as function, as followed by the atomic type, forces what is in the bracket to assume a particular vector type. The is function asks the question, is this a double, for example, and the type of tells how to tell you specifically what type of vector is this. And we're going to wrap up in a bit with this, and we're going to talk about the atomic operators. And I want you to pay attention to a few, especially I think the last two of thereabout. When you want to do addition, you use the plus sign. When you want to do the subtraction, you use minus as expected. Division is the slash, the forward slash sign. Multiplication is the asterisk. Exponential is the caret. So if I write 3 caret 2, that's 3 raised to power 2, which will give me 9. Right? So that's for the exponential. Now, there is what we call the integer division. So the integer division tells me that if you recall when we used to do mathematics in primary school, when they say something like 9/2, tell me the whole number, leave the remainder, this remainder, this, all right? So the integer division tells you the whole number and throws away the decimal points, all right? So if I do something like 9% 4/5. So that's going to be 9/5, which is 1, remainder 4, right? So it's going to give me the 1 and throw away the remainder. All right, so it's going to give me the whole number. And then if I remove the slash in the middle, it's going to throw away the whole number and give me the remainder, right? So this is going to give me the remainder 4. All right, so that's how you also can get your whole number from decimal when you're doing divisions and you want to, you know what, give me the remainder, or you know what, give me the whole numbers. You can use this particular arithmetic operators. Of course, greater than sign is our this sign, greater than sign. So you can say 5 greater than 3, which is going to give you true, because yes, 5 is greater than 3. You can check for 5 less than 3, which is, of course, will give us a false, because 5 is not greater than 3. And then we can check greater or equal to. So again, it's not like what you write in Word or any other text editor where there is a special greater or equal to. Here in R, there's no special sign. It is just greater followed by equal to. All right. So if I say this, I'm going to have it 5 greater or equal to, of course, 10/2 is 5. So 5 is greater or equal to 5, which is true because it's the same thing. And then this one, the next one is this, which is also true because it's about the same thing. 5 is less or equal to 5. All right. Now, we've talked about this before. Equal sign checks whether what is on the left is equal to what is on the right. So I can say 4 equal 2 times 2. Definitely, this is true. And I'm going to get the proof. Recall, we said be mindful when you have real numbers, team numbers. The moment you have a division or a square root that has multiple decimal points that you need to approximate, then become careful. For example, we know that pi 22/7 is just approximated to 3.14. But in the real sense, the number of decimal points continues almost indefinitely. So I will have to approximate it, which means that if you do 22/7 multiplied by 7, it's not really good. It might, and you're testing that is equal to 22, it might just tell you, no, it is not equal to 22. And which is what we just want to do right now. Is this equal to 7? Double equal sign. And then you can see that R tells me it is not equal to, because 22/7, you have to approximate it. It's an indefinite number. So be careful of that when you use the equal sign, right? How do you write not equal? You just put an exclamation mark in front of your equal. So if I say this, 4 is not equal to 2 times 2. Of course, it's a false, because false is equal to 2 times 2. So this will give me a false. All right. So again, not equal to is exclamation mark followed by equal. That's how you write the not equal to sign. The not true, the negative function is just the exclamation sign. So if I write not true, then I'm practically saying it's a false. So it gives me false. All right. So we'll be seeing a few of these things in action tomorrow. This not sign, not equal to sign, double equal sign, or is this horizontal bar, this vertical bar, which says, this example asks us, is 4 greater than 6 or 3? So let's quickly just interpret this. 4 is not greater than 6. So that's a false, but 4 is greater than 3. Since it is or, it means that as long as it is greater than one of them, it should evaluate to true. Then this should give us a true. Because though 4 is not greater than 6, it is greater than 3. But if you use the ampersand sign for and then this gives us an error, a false, because 4 is not greater than 6 and 3 at the same time. It's greater than one of them, but not both of them, right? So these are the common arithmetic operators. The last one we just talk about is the percent in percent. Percent in percent. We call it contains. Okay, and I've given this example that I just want to use to illustrate. So I have these names of 1, 2, 3, 4, 5 people. And I'm asking, can I find these 2 names, these ones on the right? Can I find them inside this list on my left? All right. And then R is going to check and say, oh, for each of them, I'm just going to check. And it's going to give us 5 values in return. And it says the first one, no. The second one, yes. The third one, yes, that's a true. And the last 2 are also false, right? So that's the percent in percent. When you want to check more than 2 things, be careful. Using equal to may not give you exactly what you want. So what you get is percent in percent. I'll just take a moment to replace this with equal to, and you'll see what happens. And you see that you get a warning message. In fact, until recently, you actually get an error. And in the real sense of it, even this warning message, this output is not helpful, because this is really not what I want. I don't want false. Because definitely Taye and Kende are in this left-hand side, but because I have used the wrong arithmetic operator, I get a wrong result. So be careful of your arithmetic operators. Make sure you use the right arithmetic operator, otherwise you get the wrong result. So let's put all of these things that we've talked about together. In the last 2 hours, we've really talked about a lot of things, right? So tomorrow, we're going to use the data that I've simulated. The data looks like this. I'm assuming that most of us work in the development sector, so we have forms that are similar to this. The respondent or the patient ID, if you want to look at it as a research or public health data or something like that. There is the date of data collection. There is the age of the respondent. There is the sex of our respondent. We're administering in, I think, 6 different states, 1 in each of the 6 geopolitical zones of Nigeria. And then we're checking whether our respondents are married. So married is a true or false. Married, true, married, false. We're also collecting their weight. We're collecting their height. But as I see sometimes in data, we're collecting this redundant data called BMI. We already know from today's class that BMI really is a combination of 2 variables, weight and height. But this particular person has decided to also collect BMI. And as we will see tomorrow, this is something very common when you start doing analysis on the field. Many of the BMI that we have entered in this particular column were wrongly calculated because maybe the person was in a hurry and things like that. Don't do your calculations on the field. So we're going to see something like that. And then we have also taken blood pressure of our respondents. Unfortunately, this particular person that collected the data decided to write it something over something. So we will be seeing blood pressure that looks like 130/70. All right. And then it becomes difficult. How do you do calculations with that? How can you add 130/70 to 130/70? What will you get? How will you add it? So this data, I've saved it as a CSV file. We'll make it available to us so that we can work with it tomorrow. It has 10,000 rows, right? It's a simulated data. I designed this data. It's not real life. So don't worry about it. It doesn't belong to anybody. All right. And because it's simulated, it's not absolutely perfect, but it's useful for what we wanted to use it for. It has 10,000 rows. It has just 10 columns. And then we'll be working on it. Again, this data is not so clean because as you can see, there's already PMI, there's already BP. But I can tell you that it is still a whole lot better than what most real life data look like. So real life data are usually even more messy. So tomorrow we're going to be exploring these questions. How many respondents participated from each state, right? Can we do a gender distribution of the, can we plot a chart that shows the gender distribution of the respondents? Can we also plot a graph that shows how the relationship between weight and height? Again, let's not forget that we said height and weight are both continuous variables. So we want to look at relationship between two continuous variables. How many persons have systolic hypertension? Now, we have talked about blood pressure today, that there is a numerator which is called the systole and a denominator which is called the diastole, for those who might not know. Systolic hypertension is when the numerator, the value at the top, is 140 and above for the purpose of this class. 140 and above, we'll assume that is a systolic hypertension. So we want to know how many of our respondents have their numerator blood pressure higher, higher or equal to 140. Okay? And the last one we're going to do, for each gender, that's for each sex, in each state, we want to know the average age of the respondents, the average height of the respondents, and the average weight of the respondents. So these are, I believe, are common real-life examples that we see. I want to quickly run us through them tomorrow. If we don't finish them tomorrow, we're going to take the rest of them on Wednesday. So this is what practically we'll walk through. I know we've done a lot of theory today, but it is important that we have the basic understanding of how R works so that when we start looking at real life data, importing it, visualizing, cleaning it, and the rest of them tomorrow, it helps to make a lot more sense for every one of us. So what have we learned today? We've learned about how to set up your R work environment. We've talked about what tidy data are, the basic building blocks in R, the naming conventions. We've said as much as possible, use snake case. We talked about the basic building blocks. We said there are 4 common atomic vectors, the integer, the double, the logical, and the characters. We've looked at the arithmetic operators, a lot of them, that you can use them to perform arithmetic. We've looked at R functions, that every function belongs to a package, and there are several packages out there on the internet that are useful for us and that we're going to be using during the course of our classes. So this is the end of the class today. We're already like 10 minutes behind time. Yes, we're going to learn how to import CSV. We're going to learn how to export CSV. Yes. Generally, the knowledge for CSV will also be good enough for Excel. So yes, we're going to look at exporting, importing CSV, exporting, importing Excel file, even though the data we're going to be using is a CSV file. Yes, we're going to be looking at importing data tomorrow. Most of what we're doing tomorrow are just real life, working us from data science from the beginning, getting your data into our transforming, cleaning your data, and other things. So a few questions that have come up right now. Yes, some people may want to revise today's recording against tomorrow class. I hope our presenter will be able to do that for us. But one thing I can definitely guarantee is that I'm going to put the slides for these 2 sessions today again in the chat box so we can have access to them. So you might just want to copy them directly from the chat box right now. So this is the first slide presentation. This is the first slide. And the second slide is coming up in a bit. Right. So this is the slide. This is the link for the second slide. So I'm just going to take a few minutes now to look at some of the questions here. I'm getting the recording of today's session. I think the poster said that we'll get the recording of all the sessions after the theory classes. But again, we already have access to the slides, so please take your time and look at them ahead of tomorrow. Bodine is asking to kindly explain the difference between library and install.packages. So install.packages is what you use to get the package you are interested in from the internet. You use that to download a copy of the package onto your computer. So ordinarily, you should do install.packages for a particular package only once. But like I said, every time you close and open your R only keeps in memory those packages that are pre-installed, right? There are only a few of them. If you want to use packages that you yourself have installed, you will have to call the library function to say, make these functions in this particular package, make them available for me to use. So you will load that library. So every instance where you open a fresh R or R Studio environment, you have to call that library before you can use that function. Okay? Which one comes first? Of course, you install packages once, and then every other instance where you want to utilize the package, you call the library function. We're going to see more of that tomorrow, right? The percent in percent is the same as subset. Not really. Subset creates, a subcopy, but percent in percent checks whether it is true or false. We're going to see a little bit more about it tomorrow, hopefully, but percent in percent is not really the same as subset. You switch between 2 projects in our studio. All right, so I'm probably just going to do that right now. Okay, so that question is coming from you. If I come to my file option here, I can either go to recent project and I can see for me all my recent projects. Yeah, a lot of them. Or I can go to open projects and then I can navigate to where my project is and open a new one. So that's how you switch between project in Art Studio. Or better still, I can go to my folder directly. Okay, so I'm going to stop sharing this screen. I'll go to a folder. Any folder that has this hexagonal structure, this diamond-like structure, if you double click on it, it's going to open that particular project in Art Studio. So that's basically how you start a new instance of project in Art Studio. Okay. How do you bring up your editor window to look at me? So I'm going to stop sharing this and I'm going to go back to my editor environment. Okay. So I'm going to close this. I believe you have something similar to this, to Lulokwe. So there are 2 ways you can bring up your editor window. If you have a .r file, and you click on it, it will automatically open your editor window. If you don't have it and you want to start a fresh R script, just click on the plus sign here. And then you say you want to open an R script, and it's going to open your editor window. So that's how you open up your editor window at the developer. What advice can I give with regarding to learning R? I think you should be tenacious, like I said, because R is a programming language, so you have to learn the language itself. So it's not really learning it. It's probably not as fast as your standard point and click software like Excel or SPSS, where all you have to do is know what to point to, know what to click. But the good thing about R is that the moment you get the hang of it, it becomes very easy to use. And because if you do routine analysis, for example, there are analysis I do on a weekly basis. Once I write the code once, on a weekly basis, I'll just run the code all over again, and then it saves me a lot of time in the end. So I think the pain of learning it is worth the stress as much as possible. The link to the slides again, I'm just going to go ahead and do that. But like I said, hopefully our host is also going to share the link to the slides. But for the sake of our participants, one more time, I'm doing it. Right, so I think these are all the questions we have for now. So for the sake of those who have finished the installation of R and R Studio and might want to get off, I think it's time to get off. We're already 17 minutes behind time. Can I just go ahead and spend the next 10 minutes, if that's okay with you, our organizer, to just show people who might be having issues with setting up their R and R Studio?
Yeah, thank you, Dr. Balogun. Please go ahead, please. Thank you. So that means officially we are done for today. Before people start logging out, I think we just appreciate today's facilitator for that excellent and clear session. We so much appreciate the so much knowledge and experience that you have distilled in a very short while. Thank you so much. So if you know you have installed your R successfully, you can log off now. We'll be in touch with you again via email, and we'll see you tomorrow. We'll communicate the commencement time tomorrow because our facilitator might be in transit. So if you don't start by 6, we might be starting by 7 p.m. West African time for the benefit of people that are joining from across the globe. So thank you so much, Dr. Balogun. So if you are fully installed and then you've appreciated our host or our facilitator, you can actually drop off, while others that want to troubleshoot their installation can wait behind so that they can receive guidance from the facilitator. Thank you, everyone. Thanks for coming. Thanks, Dr. Balogun. Yeah.
All right, thank you.